should be live. Let's do a little sound check. Mini sound check, just in a sec. Okay, that should be good. Okay. So, welcome to the ELEC3115 Electromagnetism crash course, finals crash course. And let's get started. So, just little housekeeping things. This session is streamed, it is recorded, it'll be available immediately after it finishes recording. And so, the gist of it is, if you have any questions, please let me know, scream at me. If you're online, send messages. I will be checking, will be trying to clarify everything with everyone. This is presented by myself. I'm Otto, the ELSOC Academics Exec, and it'll also be presented by Valery. So Valery is a fantastic demonstrator. He did this whole crash course last year, which was rather fantastic, and we've got him on high frequency this time around. So without much further ado, let's go ahead and just talk about a little content, like little pre-exam content. So main things to note, I mean, we all recognize that we have our first and second postulates of of the fundamental theorems of electrostatics and then magnetostatics, and then you have your time-varying magnetic field equations. The main ones we're going to be referring to, yeah, what's up? I do have to unfreeze that. Thank you very much. Let's do that. Just a sec. Bam. There we go. Okay. Fantastic stuff. So, we have our general postulates, and running through them, there's a fair bit of understanding to go in place. Rather basically, we have electric fields, which they just make divergence. Okay, so the main thing about them is there is no curl, so it doesn't rotate in any sense, it just diverges, and it diverges according to your charges. So we say that the div of your electric field, so that's the dot product of the delta, is going to be equal to your charge density over epsilon, your permittivity. Okay, this comes up very much in terms of just how we go ahead and identify solutions for certain electrostatic problems, but more importantly, we have the divergence theorem. Just a little vector calculus sum up. So we have the integral of your divergence of your electric field is going to be equal to the integral of your surface of your electrical field against said surface. So this is just the way that we quantify our charge extending outside of a region, the electrical fields extending outside of a region, which equates to the total charge enclosed of that field. Main things that should be mentioned is mainly just polarization stuff. Couple notes from the midterm is just after speaking with Rukmi, understanding is something that we really want to build in this course rather than just here's the equations, here's how we apply them, but what does that mean? Okay, a big point is going to be made out of this first question. Mind you, the questions I'll be running through are from the 2024 past paper. There are a couple of questions that are very, very finicky in how they've been worded or how they've been solved on the Moodle. In some instances, the question is just incorrect. So let's go ahead and look at how this goes. We'll begin with question 1. Questions 1 through to 3, I believe, are to do with part A of the course, and so I'll be running through those. Question 1, typically electrostatics. Let's begin. So we have part A, part I. We're going to define polarization of a dielectric material and how we relate that to the polarization vector. This was a question in our midterm, and so the way that we want to think of it is very much from the fundamental, okay, what is a what is a dipole? What is it that makes it polarized? And then how does this move into the polarization vector? So let's just note that a dipole is given by, well, an electrical dipole is given by this little equation over here. This is referring to your, I believe it's atomic dipole, your charge, and then the distance between charges. Now, what this really means is within some manner of dielectric material, we have that, actually I'm just going to stop using this, we have that the charges are bound. Charges are bound to that molecular structure, and therefore they cannot just freely flow like a conductive material. So we end up with a positive and negative kind of pole that are stuck together but within a certain distance. That distance is given by d. Now, this can be very difficult to go ahead and try and quantize and measure, and it brings into the use of the polarization vector. Okay, so right here I've used the little p, and so we use the big P as the polarization vector. We denote this to be the summation of our all your dipoles over a volume. Okay? And its unit is in coulombs per meter squared. So the way that I like to think of the polarization vector in this sense is within a medium, let's just think of some vertical strip of atoms with dipoles. There's an electrical field applied to them, and so they're going ahead and forming dipoles within them. Okay? Now, within this region, I'll just draw pluses and minuses. Within this region, we see that a field is made. However, why is it coulombs per meter squared? This is denoting a surface charge density. The reason is, at the surface of whatever medium, we can only really denote, okay, there's this net charge at the surface, and within the material, all of this kind of equalizes. And that's why when we divide by the volume, something to take note of is summing all of these, I guess, beams. There's a better way to explain this. Summing all these beams, you kind of get all these strings of dipoles, and so by collapsing them in the, I guess, going into the medium, you fix a certain charge density at the top and charge density at the bottom, which are along the surfaces. This is very much different to how you might try and explain it through using electrical fields. And yeah, so just jumping back to the question, we have dipoles. Dipoles cause polarization because they're bound, they have a positive end and negative end, and then you're relating this to the polarization vector as the summation of these per unit volume. And that gives a surface charge density that we denote typically by PP as the polarization equivalent charge density. All right, so that's question 1. Let's move forwards. So question 2, it wants us to go ahead and, using the relation of the polarization vector and the bound charge density given by rho P, show that the electrical permittivity of the dielectric material is given by epsilon r equals 1 plus fancy susceptibility, and epsilon 0 is the permittivity of free space. So from this, what we need to go ahead and gather is that just initially, our first postulate dictates that the divergence of our electrical field is going to be equal to the total charge density, so I'll just note total over epsilon. And in this case, we'll use epsilon 0 here. Now, this P total is needing to account for the dielectric bound charge density. So we can denote this as rho plus rho P, all over epsilon 0. There is an accounting of bonus surface charges because of the dielectric. Now, within this dielectric, we can then apply the equation provided of minus div P. And so we say div E is equal to rho on epsilon 0 minus 1 on epsilon 0 of the divergence of your polarization vector. When we go ahead and rearrange this, we get the total divergence. Mind you, divergence is distributive, so we can work it backwards to this state is our charge density over epsilon 0, and then just work this through, understanding that we want to equate this to our epsilon r form. So let's go ahead and plug in, oops, that was strange. Let's plug in our formal definition of our polarization vector in terms of our electrical field and group out the terms. So we get the divergence of your electrical field multiplied by 1 plus epsilon 0 times your susceptibility over epsilon 0 is equal to P on epsilon 0. And from here, we can very nicely understand that your divergence dot E is going to be equal to your charge density divided by epsilon 0 times 1 plus epsilon 0, 1 plus gamma E. And so, relating this to our relative permittivity, we can consider this factor also being equivalent to epsilon r. So this is how we equate these, just by rearranging our divergence formulas, and it arrives at epsilon r equals 1 plus your susceptibility of the your electrical susceptibility, So that's how we arrive at this. It's a very mathematical approach. It's very much built off of the understanding of your total charges accounted for right here, which will include the equivalent surface charge density built by your polarization vector. All right? How do we feel about that? Yeah? What's up?
When we get to the step, second last line on the leftmost side, how did we get, is that KE, like the symbol?
Oh, talking about this, right?
Yeah.
Yeah, so this is the susceptibility thing, which is like the big X. So how did we get there?
Yeah.
What we're substituting here is your polarization vector is equal to your susceptibility times epsilon 0 times your electrical field strength. Okay?
Gotcha.
And I've just grouped the terms there. All right? Your epsilons end up canceling and you just get the electric susceptibility. All right, good stuff. Now, that is part II of question A. Let's go ahead and look at question B. So, looking at question B, part I, what we want to do here is we're given a parallel plate capacitor. Fantastic. We're given the dimensions of it, and then there is also a certain paper that insulates the two plates. All right? Now, we're given the relative permittivity of the paper and the dielectric strength. Recall, dielectric strength is the maximum electrical field strength that can be passed through that medium without breakdown. Okay?
So breakdown occurs as soon as you reach that. And, all right, so let's calculate the following values. So first we have the capacitance value. So let's just recall C equals Q on V. Q short, V short, we want to be able to calculate these values. We have a parallel plate capacitor. We could just use our data sheet to do that, but let's just potentially focus a little bit on the derivations behind it. So V is given by the negative integral of E dx, and then E, depending on the scenario, can be determined. So we have a parallel plate capacitor, and so we can understand that the charge density at the top will be forming a Gaussian surface going through down to the bottom plate. And that's how we approximate the electrical field within a capacitor. We consider it to be completely constant between the two plates. So we say that using the first principle, we have the surface integral of your electrical field dot your surface is going to be equal to your charge, so charge enclosed, over epsilon. Note that the surface that I'm referring to here is going to be referring to, okay, let's consider the charge enclosed in this top plate. If I go ahead and consider the surface given by a large rectangle surrounding it, and I assume it's a Gaussian surface, so it's sufficiently wide enough compared to its depth, I can go ahead and just determine that the integral is going to be equivalent to the magnitude of my electrical field strength, and then the surface integral is going to be equal to 2 times the area. Okay, so we have a bottom area and then a top area. Because we're assuming that it is sufficiently wide, these fringing effects can be neglected. Okay, so that's how we're going to consider this. And so let's go ahead and determine the area. Area is going to be given by 35 millimeters wide and 2.5 meters long. So we get your magnitude times 2 times 0.035 times, was it 1.5 meters long? 2.5 meters long, all right? Is going to be equal to, mind you, this is just from the top plate of the capacitor. So we say Q enclosed 1 on epsilon, but we also need to consider the bottom plate as well. What's up?
I think I got this wrong in the midterm. Why is it 2 times the area?
Right. Okay. Yeah. Fantastic question. So, with these parallel plate ideas, the concept is that we have a positive charge at the bottom. Positive charge at the top and a negative charge at the bottom. So, if we only consider the Gaussian surfaces concerning the top plate, that's only half of the capacitor, right? That's only half of the electrical field generated by it. We need to also add on the electrical field generated by the bottom plate, okay, in this kind of understanding. How does that sound?
Makes sense.
Fantastic. All right. So, essentially, we say that the E value times 2 times 0.035 times 2.5 is going to be equal to Q on epsilon times 2. So there's 2 bits of this. We can then go ahead and cross out our multiples of 2, and we're left with E is going to be equal to Q on epsilon A. A is our area, and this is going to be in the direction of the electrical field, top to bottom. There we go. So that's the electric field. Fantastic. It is a constant value, as understood. Now we need to determine the capacitance. The way that we go ahead and determine capacitance, just remember, we first need our voltage. So V equals minus integral of E dot D, I'm going to use dr this time. And so I have my plates of my capacitor. What I'm doing here is I'm understanding that, yes, the electrical field is going down. I'm going to integrate it going upwards from 0 up to my depth D. And so this integral here will accumulate to be positive because the directions of my electrical fields is opposing. So I expect a positive outcome at the very end. I can do integral 0 to, what is my depth? Depth of my thing is 0.1 millimeters, I believe. Yes. So I can go ahead and say 1 times 10 to the minus 4. And then, mind you, I've said that my electrical field strength is constant and in the downward direction given by AR. However, I'm dot producting with dr, which I've taken to be going upwards. So I can just take another negative inside here and go ahead and say, okay, my electrical field dot my dr is just going to be Q on epsilon A dr. Okay? This supplies me with a double negative, and I'm just integrating over the length. And so typically what we get is get Q enclosed over epsilon A times D. You can see these in your formulas, your formula sheet, and it supplies us with, I mean, if anyone wants to calculate, I mean, I'll leave it as is because I don't have my calculator on hand. So let's go ahead and determine capacitance as the question had asked. We have C equals Q on V, and so we get just the reciprocal, taking away the C, the Q, sorry. So we end up with epsilon A on D as required in farads. All right, so how do we feel about that? All good? General capacitor stuff, fantastic. Now let's go ahead and consider the rated voltage. So what is the rated voltage going to refer to? It's going to refer to the maximum voltage that I can place over this capacitor without anything bad happening. Bad happening is very much going to refer to the dielectric strength, because if anything bad is going to happen, it's going to be that the entire thing is going to blow up. So let's move this working a little bit off to the side and commence the work over here. So part B double I, rated voltage. So I need the magnitude of the electrical field at the, in the capacitor to be equal to 20 megavolts per meter. Okay, so this is what I'm going to set up, and just from my previous equation, I can immediately tell that this is going to be Q enclosed on epsilon A, right? As we had discovered over here. Q on epsilon A is the magnitude of my electrical field strength. Now, note that I need to determine the voltage. So I've said that this much is going to be 20 times 10 to the 9, and so V equals Q enclosed times D on epsilon A. And so I'm just going to multiply this value by D. So I get my V max, or V rating, is going to be equal to my 20 times 10 to the, that's not meant to be 9, that's meant to be 6, 20 times 10 to the 6 times my distance, which is 10 to the minus 4. And so by supplying it with 2000 volts, I achieve breakdown and it blows up. All right, how do we feel about that? Yeah, good stuff. Let's keep it moving. So question, this one, it says that it is faulty. Customer complains that it is faulty because when 15% of the rated voltage is applied, the capacitor breaks down. Okay, and so let's think about this. We know that the capacitance nearly matched the datasheet value when measured. What could be the possible cause to such a fault? Why does the value of the capacitance match the datasheet? This feels a little bit more like an electronics question to me, but let's think about this. If anything is going to break down, it's going to break down at a certain voltage. So at 15% of the rated voltage, let's consider, so the rated voltage was 2 kilovolts. So if we take 15% of 2 kilovolts, this is going to give us about 3, wait, let me just think about this. It'll be about 300 volts. And so now 300 volts is going to imply that 300 on D is going to be the breakdown. Breakdown threshold, which is our dielectric strength for some material within this capacitance. So if we do this, remember D is just 10 to the minus 4, we end up with 3 megavolts. Now, something very important to note is 3 megavolt, mind you, this is per meter, 3 megavolts per meter is the dielectric strength of air. So we can identify that potentially within our capacitor, there is some manner of material inside of it, which is given by our paper, but then there may be some minuscule gap that is given by air. And so we're experiencing a breakdown inside this air, which is damaging the capacitor, and it is breaking. Okay, so that is the understanding that is wanted to be derived from this question. We call this little this little distance of air, let's call it dA. And now we move on to the other half of this question. We've identified a possible cause for the fault, but now we need to identify why the value of the capacitance still matches the datasheet value, approximately. And so the understanding here is we have technically 2 capacitors put in series, okay? Over here we have a fantastic one that is full of the paper, however, then we have a tiny one that is full of the air. Now, something to note here is we're adding one capacitance to another in series. We note that capacitances add in parallel. They add in, I believe it is called harmonically. So we say that CEQ equals 1 on C1 plus 1 on C2, all inverted, okay? All reciprocal. So we can identify that this value here, mind you, is going to follow the same manner of epsilon A on D, I believe. Let's figure that out. Yep, epsilon A on D. This D value, dA, is very, very small, okay? We can note that this value is very, very small. So the capacitor 2 is going to be a massive manner of capacitance. It's going to be near infinite, just if we take this kind of limit over here. Understanding that, taking C to be near infinite, this goes to 0, and we're just left with, C1. This is the understanding here, and the reason why the capacitance is going to be very close. How do we feel about that? All happy so far? All right. So that's general stuff for question 1. Fantastic. Good stuff. Let's go ahead and think about question 2. Question 2 is a bit of a head pounder. So let's go ahead and think about that. Shift this stuff all over here. Starting question 2. So question 2, part A. Part I. So we're given a two-wire transmission line with identical cylindrical conductors. This is how it's modeled. It has certain dimensions. And now we need to identify the capacitance per meter between the 2 conductors and which method we use to calculate this. Now, this is a deceptively hard question. The reason being that there are like 3 different ways you can try and approximate the capacitance for this question. Now, typically whenever it says which method did you use to calculate it and why, they really want you to use method of images. For any time, anywhere, they want you to do that. Now, I suffered a little bit on this question as I was preparing, and essentially the idea is, can you just go ahead and say that, okay, given these 2 centers of the cylinders, can we use some kind of method of images, say that, okay, the electrical fields, they are at in superposition, and therefore we get some manner of generalized capacitance building between these 2, which would give us a nice formula. However, something to note is because we have two, I guess, conductive objects here, typically when we analyze just one cylinder, we assume that there is an equal dispersion of charge around the surface. This is one of our main assumptions for electrostatics. However, because we've added a second conductor, that's no longer the case. We have lumping of charges closer to the other one because there is some manner of attachment between the two. All good?
Is that where the assumption that we have to put as much distance between them as possible so that...
Exactly. So this effect of the charges clumping together when we have two close conductors with different charges, this can be, I guess, moved away. It can be chucked out the bin if we assume that they are sufficiently far enough away from each other. So if this effect is negligible. However, in some circumstances, this will not be the case. We can note right here that your distance between these two is center to center, 4.5 millimeters. However, the radius is 0.5 millimeters. So there's a factor of 10 in there, which is not really the best. We usually like a lot more than that. But for the sake of accuracy, we can try and determine it accurately. And if we were to do that, what we would need to do, I'm not going to do it completely, just because it is a pain in the pants and not really the best thing to identify. We can identify a displacement given by B for where the net charges would, I guess, kind of conform to within certain Gaussian surfaces. And so taking this point B away from the center, mind you, this is B, the total distance is R, and then distance to this barrier we would call D. Using our method of images, we can determine that, okay, this circle given by the cylinder cut in 2D, it is going to be equipotential, okay, because it's a conductor. So that's one boundary condition we need to satisfy. Another boundary condition we need to satisfy is along this vertical line between the two conductors, we're going to have an equipotential of 0 volts. By doing this and applying method of images, we can get some fancy equations. Mind you, it does get super convoluted and people on YouTube are not the most helpful with that. So what Rukmi has done, which I guess is going to help everyone out, is she kind of hit it just at the bottom of the formula sheet. She just put it there with no real no big ceremony, no big, I guess, alarm bells. So we're going to apply this big thing. Now, just to make sure we double down, we're saying that the capacitance, let's not make a mess. Okay, one note moment. Capacitance is going to be equal to this thing when you have two manners of cylinders with charge running through. Okay, so this is the capacitance between them. We can approximate this a number of times in a number of different ways, but using method of images, because we're accounting for certain boundary conditions on the circle, that's where we get that from.
That explicitly only works if there's charges going through. That's one of the... for that?
Yes.
For that.
Yeah. Yeah. Because you get different charges accumulating on different sides. Okay. So it's part of the same kind of network. Okay. So just we throw in a little from formula sheet. Mind you, the solutions do this as well, but with no explanation. We say that C equals to, I believe it was epsilon pi on ln capital D on 2a plus the square root of capital D on 2a all squared minus 1. There are some very nice derivations of how this works just on YouTube, but they all kind of revolve about, okay, here is the boundary condition for this left circle, and then how do we fit that together? Which can be nice. It gives you something of a polynomial. I think when I tried it this morning, it gives you a cubic polynomial for B, which a little scary. Anyways, so there we are. That is the capacitance there. That is what we get as the most accurate form for this type of question using method of images. All right. And the reason why we use this method of images was so that we could account for the boundary conditions and the, I guess, the mirror image drawing each other together, displacing the, I guess, central charges of both of these materials. Okay? Very interesting stuff. Let's move forwards. Now we have this question over here. Question II. The line conductors are made up of copper with a conductivity of 5.6 times 10 to the 7 Siemens per meter. DC voltage source is applied at the load, is supplying a load of this. Calculate the current and then the load side voltages. So, let's not make a mess. I'm going to say that a lot. So, we're given that UG, which is generator, which we can see just over here, is going to give 55 volts. Now, something important is they've given us a, I guess, acceptance through the wire, a conductivity, okay? And so, we understand that the resistance of a wire is going to be given by the length divided by the conductivity times by the surface area, okay, of the cross-section. And the reasoning of this is just so that you can understand there's a material property, there's a dimension property, and there's another dimension property. So resistance should accumulate as distance increases, because saying that having it longer would give it more conductivity wouldn't really make all that much sense, but it can be confusing from the units given. So applying this little tidbit of knowledge, we can go ahead and say, using a voltage division, we can determine what UR would be, which is the load side voltage, and we can also determine the current. All of this through just voltage divisions, okay? And just V equals IR. So we say that I equals V on R total. R total is going to be equal to, we have RL to be 55 ohms, 55 plus 2 lots of L on sigma S. So L, the length of each of them, is going to be given as 45 meters. The conductance is down here, and then the cross-sectional area is given by their radius, 0.5 millimeters. All right, so let's do this. 45 meters on, I believe that was 57 times 10 to the 7 times 0.5 times 10 to the minus 3, so half a millimeter squared times pi, because it's assumed cylindrical, and there we go. That's the total resistance. 5.6, my bad. There we are. And there we have it. That is going to be our value for total resistance, and when we do the voltage divided by that value, we get the current, and if we want the UL, I believe it was, UR, my bad. This is just denoting the voltage over that side resistance over there. We can just go ahead and do UR equals to UG times 55 on R total. Fantastic. Any questions so far for this bit concerning, I guess, conductances and such? All right, fair enough. There's a couple duals that we should consider here with magnetic circuits, which we can note from R equals L on sigma S, and then the reluctance being equal to L on epsilon S, I believe. Oh, sorry, not epsilon, mu. That's more like it. So this is for our magnetic circuit, just this one. So we can consider certain duals of equations to consider the circuit, the magnetic circuit equivalences. All right, anyways, let's keep moving forwards. And so that's part II. Now there's part III. So this is a little bit of a strange one, but let's go ahead and handle it. So we're given a current to establish a magnetic field. That's what we've calculated. And therefore, an inductance also forms, right? We want to go ahead and determine the inductance per meter of the given two-wire transmission system. So let's go ahead and do this. Let's just highlight the question right here. So the idea here is we know that the inductance L is going to be given by, I believe it was mu0 on 8 pi plus mu0 on 2 pi times the natural log of d on A. Just generally, this is determining the internal inductance and then your external inductance. The internal inductance is within the wire we observe certain magnetic fields of varying strength as we go towards the outside of the conductor. And then the external inductance is concerning that, I guess, external to the inductor. So something very important to note here is D is arbitrary. Our distance D is arbitrary. Why is this? Because our inductance kind of needs to expand to somewhere. Whenever we talk about inductors, we're talking about the total flux generated by them going outwardly. So typically this is done nicely within some manner of coaxial, where you have a defined bound, where you have your initial conductor, your dielectric, and then your other conductor. And so you just need to consider the inductances internally inside this dot here and externally inside this dielectric. However, we don't have a very nice external bound here. What we have instead, I'm going to draw it like this. Here's our top line, and here is our bottom line. Something very cool is if I draw a circle, I can apply the, I believe it's Ampere's law. So first or second postulate of the magnetostatics. And what that really says is that my integral, my closed loop integral, mind you, of, let's say, a curve, so curve C, of my magnetic field, B dot dl, is going to be equal to mu times I enclosed. So if I have a net zero enclosed current, I can say that the total flux through this loop is going to be 0. Okay, so that's the equivalence I'm seeing here. So as soon as, let's say I'm imagining this conductor here, I draw loops, so I draw loops, so I draw loops. If I draw any greater loop, I'm including this conductor at the bottom. The bottom conductor draws current back and is going to change how I analyze this. So the external inductance I'm referring to is just going to be up to this point. For the sake of this question, I'm going to go ahead and say that it's just going to be the 40, wait, I believe it's given somewhere, 4.5 millimeters between them. So I have 45 millimeters here to there, which I'm going to put as my D value. So this implies that D is going to be 4.5 millimeters, which is the center to center measurement. So this determines the greatest distance at which I am considering a magnetic field to be generated by this transmission line over here. Does that make sense? All right, so moving forwards from that, I can substitute back in. Mind you, I have 2 of these inductors, and so I'm going to be doubling my values in total, right? Because they are all in series, I add them in series. I'm pretty happy with that. So L total is going to be equal to mu0 on 4 pi plus mu0 on pi times the natural log of 9. Mind you, because A, the internal resistance of the cable, was 0.5 millimeters. Fantastic stuff. All right, fantastic. Mind you, they did ask us to ignore the mutual inductance. If we didn't in this system, there would be a couple messy things. Mainly because we're looking at the amount of flux that would, I guess, incite other currents inside this wire, which it's a little messy. It's more nicer when we have coils linking to each other, because then you can observe a very nice sharing of flux, as opposed to this, where it's kind of like, oh, you're moving in one way, you're moving in the other way. Let's just think of everything moving to the left inside here, which is what it would typically be, just because that's going to be where flux is shared, going in the same direction between these two transmission lines. That's the word. All right, let's not get too far off topic. So that's that, and now we're given another task. Question part 4. Draw an electric circuit showing the resistance, capacitance, and inductance, all units per meter, of the two-wire system in this. Mind you, I should probably put a Henry's per meter. Don't want to get fact-checked by that. So, the electrical circuit for this. So, there are a few things to note. We have a capacitance, an inductance, and relative resistances, just by the conductance of the circuit. So, just looking into the circuit, first thing I'm always going to see is typically a capacitance. This is just the binding of the top and bottom transmission line channels. We have the resistances given by the conductivity of those transmission channels. We could try and potentially break this down into portion by portion as we would in high frequency. However, I guess for the sake of this question, they really just want to see where what goes where. Something the answers for this document do, which I'm not the most sure on, is going to be chuck the inductor in parallel with the load. Now, something very funky with this is that this is the inductance of the transmission lines. They're linking together, they're in series, so it is very much questionable to why the answers would do this. It's not correct. It should be in series. It is just blatantly incorrect. So the solutions for the document are just incorrect. It should be in series. This is how we do it in the high frequency model. In the high frequency model, just recall, you'll be able to see it potentially a little later. You have your characteristic impedance, well, sorry, not your characteristic impedance of the line. You have a resistance of the line followed by some manner of inductance through it, and then a capacitance to the other channel. And this scatters onwards until you hit your load resistance. And so, mind you, for lossless cables, we get rid of this resistor, and that's that. That's our approximation. That's how we get characteristic impedances and such. Let's move away from that, because that is high frequency. This is what it should look like. We get resistances, we get inductance. All these elements behave as they should when they are in series. So, we put them in series. Fantastic stuff. The only thing that happens between the lines is the capacitance. Reasoning for why it's before and not after, it gets a little touchy, but
it can be in both directions actually.
Yeah. So like you could also put it here. Yeah?
Yeah.
Yeah.
It does matter.
It does matter. Yeah? Doesn't matter?
Yeah, because the whole system is distributed. It's a distributed network. So it's not at one single place, it's all along the line.
Yeah. So as we mentioned, you get it everywhere. It's along the entire line. So this is an approximation model. So that's happy. Anyways, that is nearly this question done. The rest of the question is in part B. So part B, let's just read it out. So we have a capacitance and inductance between two conductors. Mind you, we see that certain forces are acting on them. Now, I believe for this question, the type of thing that they're referring to is going to be, you have they don't specify super well, but they want you to chuck it in terms of the above scenario. So we have the scenario of transmission line into resistance, into another transmission line. Bam. There's a certain capacitance between them, which is going to promote some manner of imaginary force, okay? A force that we consider by the virtual displacement theorem, okay? So virtual displacement theorem gives us something in terms of the change in energy depending on your shifting of the scenario. So, some things to note. Let's go ahead and actually just move all this, or maybe shrink it, just because it's going to take up a lot of space. So, let's just move that over here. Out of sight, out of mind. Now, we have question B, part I. So, we want to consider the electrostatic force between the two conductors for the values of X, A, and a constant voltage. Now, something to note here, mind you, we're talking about energies and forces and such. It is a constant voltage. Mind you, a constant voltage over a capacitor will imply that there is some manner of source. Now, this is very important. Some insight that I will provide here. Just if we consider energy, if we have energy reaching a maximum point here, so this is my WE, this is the size of the vectors, the rate of change going into it. It slowly dwindles and then it decreases. So if I consider the div of my, the gradient of my energy field, then I can say that, okay, going forwards, it decreases, okay? And so if it's decreasing, then, rate of change is going up as I'm going forwards, meaning I go forwards, I stop, and then it's going down as the rate of change descends as I'm moving away and getting a smaller value. Okay, so we get a manner of maximum energy here. So a source is supplied and it is holding it at a high energy point. So this is how I like to visualize it, as opposed to a low energy point, where we say that, okay, let's consider the div of our energy. It goes down less, stops, goes up a lot. As I'm moving from left to right, then I have down multiplied by positive in that direction, which will give me a negative value, then it'll go to 0, then in that value. So in this scenario, if I am keeping it in place, then all it says is that there's no supplied voltage here, and so in this scenario, I would have minus gradient of my omega E, of my energy, and here I'd have my positive gradient of my energy, just because of certain field stuff that you can go ahead and double check for yourself. So all that says is if source, use F equals the gradient of your energy. If no source, then use F equals negative of your gradient. Okay? So this is the manner of virtual displacement forces that we are considering for these equations. So we can see here that yes, a source is supplied because we get a consistent voltage drop over the capacitor, and so let's just remember that the energy of the capacitor is given by a half of CV squared. V is constant, so we say that Fx is going to be equal to 1 on 2 V squared, and we're going to do dc on dx. Now, why have I done this? Essentially, to take the gradient, I'm going ahead and I'm saying, okay, let's consider the vector of dwe on dx, dwe on dy, dwe on dz, And I'm assuming for this scenario that in this capacitor, it's how far away I am from the top. And so I can go ahead and say, okay, if I move in the y direction or the z direction, it's not going to change at all. So my derivatives there will be 0. And so I'm just considering in the x direction, which is going to be towards the other plate. How does that sound? All right, so let's go ahead and look at our capacitance equation, which was spoken about previously. We're talking about previous parts of the question. And so we end up with this. Actually, wait, is that right? I believe that is correct. Nearly correct. Wait, give me just a second, sorry. So we have, the big ln that we approximate. Yes. So we're assuming for this scenario that we're going to be working with C equals epsilon pi on ln capital D on A. Okay? So the reason we do this is just because the ln of the D on 2A plus the square root of D on 2A all squared, I didn't need that, minus 1 is going to be approximately equal to, the derivative is a lot more difficult to compute, and they've given us a little example on how to go ahead and differentiate the 1 on ln, which is the approach that we're going to take. So we get the fx is going to be equal to 1 on 2 v squared, and then epsilon pi, double check over here, we get x ln squared there. So on epsilon pi on x, then ln x on a squared. All right. That's that. That is our electrostatic force there. Bam. Now we need to go ahead and determine, for part 2, the electromagnetic force per meter, okay, between the two conductors. So, once again, I'll just tap on 2i. We know that, okay, let's go ahead and think about this. In the question, it is saying, given a current found in the part above. So again, we're assuming that there's a supplied current, so we have an active source. So we're going to use the positive gradient of our energy. So this time, instead of x, let's go ahead and use L is going to be equal to 1/2 Li squared. This much is constant, and so we get gradient of this thing. So we get 1/2 I squared times dl on dx. Now, the interesting thing is, we got that equation given to us right over here. We do have to multiply it by 2 because we have 2 inductors per meter, I suppose. And so we just need to take the ln over there. So let's move over here. We get equals 1 on 2 I squared times d on dx of mu 0 on 4 pi plus mu 0 on pi ln d on a, x on a I'll have. And so, no x terms here, differentiate this. They tell us that the ln just becomes 1 on x, and so we get 1 on 2 I squared mu 0 on pi times x. Bam. All right, that's a bit of energy equations for us. And let's try and just very quickly hammer out the rest of magnetostatics. How does that sound? Any questions for this part so far? All right. Okay, let's do this. So, I'll actually drag this down a little bit. So, question 3. Let's talk about part A. We're given this figure over here. Mind you, it is a terribly drawn figure by whoever made this paper. They actually drew one of the coils the wrong way around. So I'm going to use the diagram as it looks. which is meaning that the solutions are going to be a little bit off from what you might be expecting, which is greater relevance for this little session. So let's, without further ado, think about this. So figure 2, magnetic device has 2 air gaps, 2 coils, depth of that, yada yada. It has an infinitely permeable core. Now, all this really means is if I check my reluctance equation, reluctance L on mu S. If mu goes to infinity, there's no reluctance there. It's just a wire, okay, in my magnetic circuit equivalent. So let's go ahead. We look at A part I. We need to draw the magnetic circuit of the device. So as per usual, let's think about this. If I'm going ahead and I'm making a coil, I know the flux is going to go in one direction. Now, something to note is I don't really like using a current source to do that, because my current is my flux in this scenario. What I'm going to do is it's going to be something of a voltage source. And since the flux is going upwards in this scenario, just note over here, right-hand rule, we love it. We're going to go ahead and say that this source given by N1, I1 is going to go and generate a current upwards, okay? And so we put the positive terminal facing downwards. We have an immediate resistance or reluctance, another one as the gap, mind you, because the mu is infinite within the core, we go ahead and put that as just a straight line, and then we're met with another coil. Now, something funky about this coil is that they do it wrong in the solutions, but I'm going to use it like this. We see that the coil is wrapping around this way, we get current going down, that means we put the positive end on the top, okay? Because that way, if I just have that source, the current's going to go top to bottom. Does that make some sense, yeah? All right, so plus, minus, there we go. So there we have our magnetic circuit. Let's not forget to label N2, I2. Remember, what is flowing is going to be your flux. This is the reluctance G1. This is the reluctance G2. All right. The next part of the question is going to be to determine the, using the currents, number of turns, and dimensions of the thing, find an expression for the flux density in the air gaps. So we're going to have to use some manner of, I suppose, assumption here, and that's going to do with the, the distribution of the flux density in those air gaps. We're going to have to assume that it's a uniform density. So first things first, assume uniform, I can't spell, density of flux in the gaps. Oops. And we know that phi, as our just flux, is going to be equal to, mind you, this is our current. We're going to just use I equals V on R. So V is going to be given by N1, I1 minus. So there's a double negative here. So minus the negative of N2, I2, because I'm considering this to be my ground at the top. It's very funky. What's up?
A question. Can you please elaborate on direction of the voltage sources? Because I can't see properly, but I think if you look at the right hand rule, the left coil should generate flux upward, and the right should also generate flux upward, correct?
The right one would generate flux downwards. So something to note is they've actually put it, it's a very funky drawing. So what I'm going to consider it as is we go out the back like that. I think they're very, very, it's very close. It's very close. It's not a good drawing.
Isn't that wire supposed to be at the front and one at the back?
I don't know.
Okay,
and so for this sake, I'm going to say that it comes out the back. Okay. Let's say it comes out through the back, and so we use thumb goes down. Okay? So that way we get, yes, they are oppositely sided.
What did the solutions have it?
The solutions had it as, as Valerie said, with it going up, which I don't like how they drew it. It was very confusing, and
It's up to interpretation.
Yeah. This way I get to cover. Oh, why is it positive, not negative? Which I find to be a little nicer. But let's get back into it. So this is our voltage at the top. We've taken double negative. Sure, it's almost as though these two coils can join together and just cause more loops, which would be very cool. But let's move forwards. We have our total reluctance, which is going to be reluctance G1 plus reluctance G2. Remember, L on mu S. The distances of those gaps are they given? I don't think they're given. Yeah, they're just relative. So we're going to say, okay, that is fantastic. L equals E1. That's not meant to be epsilon, E1 or E2. S equals, I guess, the cross section. And then mu equals 4 pi times 10 to the minus 7, because it's just mu 0. Okay? There is no relative permeability here because it's air. It's an air gap. All right, so that gives us flux. Now we get something very funky. We need to talk about density. Remember, I said assuming uniform density. So we get B. B field, I guess in magnitude, is going to be equal to N1 I1 plus N2 I2 on, remember, our susceptibility, sorry, is that our susceptibility? The cross section, that is going to be divided here. So flux on S is going to give me B. So I'm dividing everything by S. So I need to multiply the denominator by S. So I get E1 on mu 0 plus E2 on mu 0. So I can just factor mu 0 out and la-di-da. All right, fantastic stuff. That is the flux density. That is that question, I believe. Yeah, all right, in the air gaps. Good stuff. Now, something to note is, once again, we are assuming that it is all going through the material rather than losing some of the flux, which would alter our answer slightly. So let's move forward onto another question, unless anyone has any questions. Fair enough. Okay, so part B, we have the current in the coil is an AC thingy. We use the maximum flux density possible in the core. And so show that the RMS value of the voltage given in coil 2 would be described by this. So there's something very cool happening here. We're saying that, okay, we're using B max, mind you, that would be from the saturation of the core. So we say, let's describe B. B is going to be equal to B max, because we're assigning a sinusoid to it, times sine of omega t. And so we can say that your phi is going to equal to S B max sine omega t. That's atrocious. There we go. Where S is the cross-sectional area, so we've just integrated. We're once again assuming that it's a uniform density of your flux. And so we need to apply, I believe, Faraday's law, where we say the EMF is equal to minus N times d phi on dt. Okay, this is the most typical one for them to use. Not to say that they can't use other ones to trip us up, but this is the one we see here. So we get V2 is going to be equal to minus N times S omega B max cos of omega t. So let's look at this. This is looking pretty nice so far. RMS value, so V2 RMS, the cosine becomes 1 on root 2, and so we get minus N2, because we're talking about V2. We get times S, we get times B max. Now, omega is going to be 2 pi times F, okay? So we get F times 2 pi divided by root 2. Funny thing, this turns out to be 4.44-ish. All right, and that gives us the answer as required by here. I'll put the S as SC, and we're happy. So that is that part, just done by substituting things in and applying Faraday's law. Pretty straightforward there. That's that. Now the little goofy thing happens when we go ahead and approach part C. They word this rather terribly. they word this rather terribly. And so what I'm going to do is I'm going to make up a question. So, as you do in an exam. So, we're going to go ahead and say, instead of saying, okay, this is designed to operate at this, at that frequency, in this circumstance, we work at that, this number of parameters, la-di-da, what would be the voltage at the generator if the frequency was that? What we're going to do is we're going to consider, okay, same box that does all this magical stuff. Usually, when you work it at 50 hertz and you supply it a certain voltage, you get 240 volts, just given circumstances. Now we're going to go ahead and think, okay, if instead I run it at 16.67 hertz, what would I get? Funny thing is, we get a linear relation here, and I'm pretty sure this is actually a question that ends up being described in the solution. So what we're going to say is the V that we have here, so V RMS, is going to be given by 4.44, just looking at above from the previous question, because we usually let questions flow onto questions. 4.44 F N2, let's just use 4.44 F N B max SC. Mind you, SC and B max have been determined to a maximum value. We're assuming that we're running this machine to the maximum saturation of the transformer, okay? And so we are going to apply B max, we're going to apply SC. Those are constant, fantastic. The machine is designed with a set turns ratio, number of turns, N, and we're just changing the frequency. What we're doing here, the main thing is max voltage applied to supply B max, okay, just from one of the coils. This is the main thing to look out for. So that's that. Now we need to consider VRMS in terms of F, and as I mentioned before, this is a linear relationship, and so I said 240 comes from 50 hertz, and so funnily enough, if I look at 16.67 hertz equals 50 on 3, I kind of just divide the voltage by 3 because the frequency gets divided by 3, which is rather strange. So I say 80 volts from that many hertz. It's very goofy, and it's very much understanding that, okay, are we using the same formula? This is something that is relating just transformers in general. So I think the main difficulty, main thought process behind this question is to understand that, okay, Bmax is being kept the same because we're supplying some manner of voltage, however great, depending on whatever N1 is from the other side of this machine, to saturate the core, okay? We're saturating the core, so all three of these become constants. Just going to do that in red. Your N, that's already constant, it's built in. SC, built in. Bmax is being kept constant, okay? Because we're assuming that in this operation that it is designed for, it saturates that core, okay? Which is rather goofy. Now, standard year 12 question. How eddy currents occur in the core of magnetic devices? We love this question, don't we? Okay, so explain how eddy currents occur. And very much so, there is like only one answer, unless you can find a magnetically permeable, element that does not conduct electricity. I don't know how you're going to do it. So we just say eddy current because conductor. Full marks right there. But mind you, let's think about the rest of the question. What will be the effect of eddy currents in the device? The idea is, let's just consider a big tube. Now, big tube, I go ahead and I put some coils on it, and it makes a flux, okay? So flux, I'm going to do this in a different color. Flux comes running out of here, and let's say it's oscillating, it's changing. There's a change in flux. Something that I know is that from just my what's it called? The postulates. You get your integral of a line b dot dl gives mu I enclosed. There's probably plus some j thingy when you put it into the time thing, but just understanding this, the flux generates currents, okay? And that's all that eddy currents are. So that if I have another coil in here, that's gonna generate some manner of current. But if my core is, conductive, I'm gonna generate those currents inside the core, okay? And so the main effect is there is a power loss, and that generates heat. And is there anything else? How can we reduce this effect? So the idea is that it generates currents inside the material. These currents inside the material actually generate magnetic fields that kind of like oppose the ones generating them, conservation of energy stuff. And that is going to hinder the ability of our core to work nicely and transmit energy between different coils and act as a transformer, really. So to reduce the effect, reduce by limiting, I can't spell, geez, limiting the, generatable area of your eddy currents. So limiting the depth / width by laminating. So it's, oh my gosh, laminating. So we are cutting down the eddy currents by reducing the plane in which they can generate and lose energy in. So there's less of a conducting zone for that. All right, those questions. I hope this was somewhat insightful, even though this part of the course was covered like 4 weeks ago, maybe longer, I don't even know. But hope this helped, and that is going to be part A over. I hope the stream is doing all right. Next up, I'll invite Valeria to the stage, and let's go from there. All right.
Okay, good.
So, I'll be monitoring. Should be good.
All good.
Thank you very much.
Thank you.
Yeah. Take it away when
You get the newest model over
Okay.
here. Yeah. Surely there's a way to capture videos. Surely.
Okay, I will start then. Do you want to break or something like, or should I start now? Then I'll start now. Yeah. So I will go through the second part of the course, the waveguides, transmission lines, high frequency stuff, and things like this. I will I will do like this 3 main sections, like this three main kinds of questions you can get on the exam. The first kind of question is tandem reflections. Second part is impedance matching using Smith charts, or this kind of like similar kind of like approaches, and third part is waveguide calculations, like sizes of waveguides, critical frequencies, and stuff like this. So I'll do one question from each general kind of question, and I'll use I'll go I think my first prepared question. The first one is from example 1. Actually, Otto, where are these examples from? Are they given to students? Where are those examples from? Are they given to students, right?
They're accessible to students. They're made by Danielle as just bonus practice for you.
Okay then. You should have access to those. This is the first example question. This is like a question for tandem reflections, but it's a bit more complicated because here you have 2 sections. You have two parts where you can reflect things. So normally you have just a cable, some load resistance, some source resistance, and some voltage source, RS, RL, and this Z node. And you have some gamma, some reflection coefficient gamma facing this way, gamma 1, and some reflection coefficient gamma naught facing this way. And so you can like just draw like the voltage waves in time domain going back and forth, and use the values of gamma to calculate the values of the incident wave and reflected wave. For example, if you have a voltage source like a voltage of 1 here, then the input voltage wave will be just voltage division between Z0 and RS. So V in, the voltage that the transmission line will see on the input will be just Z0 times over Z0 plus RS times V source, and then you have a wave traveling forwards. By the way, this is time axis. This is length axis. This is I will call this Z. So the wave travels along the line with amplitude V in, and then it reflects backward with amplitude gamma 1 V in, and then it goes here and then reflects backwards with amplitude gamma 1 gamma naught V in, and so on. And reflections go back and forth to basically infinity. This question is slightly different because here you have two interfaces. You have two cables with some kind of discontinuity between them. So you will have two sections where you can reflect stuff. I will quickly draw this again. So here you have two cables. You have some source resistance of 50 ohms, some voltage source of magnitude 1. This Z0 is 50 ohms, and then between them you also have some kind of resistance. And here you have your load resistance, which is 25.
Could you zoom in a little? Could you zoom in a little?
Oh, sorry.
Thank you.
Yeah. Then first thing you need to do, you need to find the deflection coefficients and transmission coefficients for this system at every interface. Transmission coefficients basically because in this example, like you only have two sides, you reflect off each side. But here you have interface in between, so you will reflect you will reflect some wave and some will transmit. So you have both reflection coefficients and transmission coefficient in the middle. So rather than if you draw your interfaces. Again, here is Z, here is time. If you send a wave through, some it will reflect and some will transmit like this. And those will transmit like this, like the reflected wave will be with some gamma V in, and transmitted wave will be with some T V in. And those gamma and T can be found by finding the power. The incident power must be equal to reflected power plus transmitted power. Actually, there's another way to find as you probably know from formula sheet or from lectures, gamma is equal to just it's Z minus Z naught over Z plus Z naught. Interestingly, T in this kind of scenario will just be equal to 1 plus gamma, and this can be fairly easily justified by looking at this reflection diagram. So initially the voltage at the interface is 0 and the load is 0. And say you send 1 volt this way, right? And the reflected wave will just be is just going to be gamma times 1 because it's just 1 volt, right? The voltage that the impedance the next line will see on its input is just going to be the sum of the incident and reflected voltage. So the voltage that the next transmission line sees on its input is the sum of those two waves. It's going to be 1 plus gamma. This is going to be sent this way. It's just an easy way to understand why this is the case. And this is also possible to derive using the incident and reflected powers. So I'll just quickly calculate all the gammas and t's. I will call this one a gamma naught, this one gamma 1, gamma 2, and gamma 3, and call this T, right? gamma naught is obviously 1 because, 0, because Z naught is 50 ohms and the source impedance is 50 ohms. So the reflection from the source is going to be like, there's going to be no reflection because they're perfectly matched. So if you see like here is 50 minus 50 over 50 plus 50, which is just 0. So gamma naught is 0, right? Gamma 1 is actually equal to gamma 2 because the situation is symmetrical. You can see if you look from left or from the right, you see the same impedance both ways relative to the same like Z naught, and it is equal to, because like if you look at the wave traveling this way from the left, it will see in parallel, it will see Z naught of the next line in parallel with 50 ohms load. So the impedance it sees is 25 ohms. It's half, it's half of 50 ohms because 50 in parallel is 50, right? So it is equal to just 25 minus 50 over 25 plus 50, which is minus 1/3. And gamma 3, if you look at gamma 3, it's actually the same. You have 50 ohms impedance of Z naught, and you have 25 ohms load. So it's actually exactly the same. It's also 1/3, minus 1/3, because it's the same load impedance. Right? Now I will draw a reflection diagram. Okay, so gamma this way is 1/3, gamma this way is 1/3, with minus sign, gamma this way is minus 1/3. And the transmission coefficient, T, is going to be just 1 plus gamma, so it's 2/3. Right? And the reflection here is 0. So what's going to happen? Like the first wave goes through, it reflects from the interface. The magnitude of the first wave is going to be 0.5. The reason for it is because there's a 1-to-1 voltage divider between this 50 ohm and this 50 ohm. The impedance of the cable is the same as the impedance of the source. So you just have 1-to-1 voltage division. Like a factor of 2 voltage division. So the impedance, a transmission line will see a half a volt from the 1 volt source. So the first wave is half a volt traveling this way. It reflects off as 1/3 of half a volt. So 1/6 of a volt, right? And it's going to terminate here. It's going to terminate here. Actually, I think I skipped part of the question accidentally, which is going to be quite important. It gives you propagation velocity. And it gives you length of cables, 1 meter. From this you can derive the time delay of the cable. So this time delay is this time step. This tau is the time delay of propagation for each cable, which can be found as just velocity over length. So like length of velocity. So tau is just 1 meter over 2 to the 8. It is 5 nanoseconds, right? So this time is 5 nanoseconds, and this I'm drawing in the wrong place. So this is 5 nanoseconds, and this is 10 nanoseconds. The cables are of equal lengths, and you can see that the wave reaches back to the start. It is going to terminate because the source impedance is the same as the line impedance. It's going to be perfect termination. So this wave just sinks into the source. It doesn't get reflected again. But this wave will reflect again back and then reflect back and transmit like this. So like those waves always terminated at the end, but those waves always will go back and forth with a factor of 1/3. So this is going to be 2/3 times half. So 2.6 volt. You can also write the currents, but the currents are just this divided by 50. Like it's going to be the same thing. Then this wave is going to be 2 over 18 because this is actually this is minus sign. This is going to be, this t is 2/3, so this is going to be minus 4 over 18 times 3 is how much? 3, 54, and so on. Like this one is going to be, and you can calculate the waves going back and forth. Like it's like in the exam conditions, it's just rather than do fractions. It's much easier to do like it's much easier to just write down like decimal values. Yeah. What is part was in? And you do this until 30 nanoseconds. So and you also the question asks to find voltages. Oops. What happened? You need to find voltages and currents. So here just draw the voltages. You would also draw the current. So like if the voltage is half a volt, then the current is half a volt divided by 50. It's 10 milliamps. Oops. And this is just 1/10. It's minus 3.33 milliamps, and so on. And you also write the currents and voltages in both directions. What else? And then this has to do this for 30 nanoseconds. So this is each reflection takes 5 nanoseconds. So do this for 6 reflections back and forth. And then you need to find the values. Then you draw like the waveform in time domain for voltage at each node. So like why is this? So you draw the voltage at VA, VB, and the voltage as a load, and you can easily find it by just summing the waves at every point. So here you have half a volt going this way and 1/6 of a volt going back. So this is just half minus 1/6, which is 2/6. It's consistently the same voltage as this. Then I just draw the voltage at the middle, like as an example. If you draw 6 graphs, so 3 voltages and 3 currents. So this is V at point B over time. So initially it's 0, then at 5 nanoseconds you get up to, at this point is 2/6, 0.333, yeah. And then as next reflection, which happens after 10 nanoseconds, so this is 15 nanoseconds, you get, this is 2 over 18, and this one is 2 over 18, 18 times 3, it's going to be minus plus 2 over 54. Right. So you add those together, and then it's going to go to 18. Is that 6 over? It goes down a little bit, and then goes sorry, around scale. So this will happen at 15 nanoseconds. It will go down a little bit, and then go down a little bit more until it reaches a steady state value. And and you can find the steady state value like the simple way to find the steady state value is if you look at this like at DC, all this happens very fast. It happens like within the first 30 to 15 nanoseconds. So all those reflections, it's going to settle to some steady state value. And in steady state, you can just pretend that transmission lines are just wires. So we just have 50 ohm here. Oops. You just have 50 ohm. Why is this? You just have 50 ohm here, 50 ohm here, and 25 ohm here. So at steady state, voltage at point B is going to be just voltage division of 50 ohms in parallel with 25, like this. And this is 1 volt, which actually turns out to be 0.25 volts. So this steady state will be 0.25 volt. And actually this same value will be, because the cables act like at DC, like at steady state, they will act just as short wires. And the same voltage will be present at VA and V load, but it will approach it from different directions. So if you actually look at the voltage at the start, it's going to do something slightly different. So at the start, it's going to start from half a volt and drop down after every 10 nanoseconds. And continue until 0.25 volt. And voltage the load will increase from 0, this is VA, and this is V load. It will stay at 0 until 10 nanoseconds as well. And then grow a little bit until it reaches 0.25 as well. All good? Any questions? No? All good. Yeah, I think this is it for this question. Come on time. Yeah, 20 minutes. Good. Any questions about this, like this kind of question? How do you do this? The other particular style questions. No questions? Then I'll just move on. Next question that I have prepared is impedance matching, which is actually question 4 of 2019 paper. Which is a fairly it's actually very similar to the question you had on your assignment on impedance matching, but it's slightly simpler because here all all the cables are the same material, so you don't have to you have no need to normalize different cable impedances. All those cables are 50 ohms. Why is this moving? All the cables are 50 ohms. You have your load impedance, which you can normalize to your cable relative to 50 ohms, and then you find you are given ER, which you can use to find the speed of light in the cable, and from there you can find the actual length. Because when you do Smith chart matching, you write all lengths in terms of lambda, in terms of the wavelengths of your radiation as this frequency, and to convert it to actual physical lengths of of cable of cable sections, you need to know the speed of light in that particular cable. So to find this, your VP is just C over square root of epsilon r, which is just C times 10 to the 8 over root of 2.1, which happens to be almost exactly I'll just write equal value. It just happens to be 2.07 times 10 to the 8 meters per second. And then your lambda is VP on F, and it happens to be 8.63 centimeters. I will need this later for matching of on the Smith chart. And one last thing that we need to do, we need to normalize our impedances relative to the cable. Where is this? Yes. So your Z is 35 minus 47.5 J ohms, and your small z, which is normalized impedance, how it's usually denoted, is big Z on Z naught. It's equal to 0.7 minus 0.95 J. Now we can move to Smith chart. Actually, before we do this, I will quickly point out a few things. This asks you for one set of solution. The reason for it is because you can create infinitely many solutions just by adding 2 pi radians to every cable section. You can make your cable sections longer by half a wavelength and still get valid matching. it's most convenient to just find one simplest solution. Sometimes you have two simplest solutions, which you need to decide between which one you need to use shorter cables, but not in this case. And then, yes, that's it, I think. Yeah. Let's go to Smith chart. So your initial point is 0.7 minus 0.95. So 0.95 is why it's this. So you find where those lines intersect. Here is your a load point. Actually, did I? No, sorry, that's incorrect.
Just a question.
Yeah.
If it's minus J.
It's minus, yes. I just noticed like this is
Gotcha.
yeah.
I was just gonna
Thanks. So it's on the negative side. It is this point here. Then I'll quickly go back to the paper and point out that you have a shorted stub in parallel, right? So there's two things you need to worry about. First, if your L is shorter than lambda on 4, then this stub is going to act as an inductance. It's going to be approximately an inductor. It will have inductive impedance. So you'll move upward on the Smith chart. But with the caveat, because you need to reflect the Smith chart on the opposite side to have conductance. Because this stub is in parallel. It's a parallel stub. So what you do, I will just quickly attempt to explain what I'm doing. Will this work? It will work. Oops. I'll just move this. Nope. This is not a good idea. How do I move this again? This will not let me move it. Okay, whatever. Attempt to draw circles.
Yeah, we got it. Then you just moved a little bit.
Oh, okay, middle bit. Okay, thanks. So this circle is your resistance equal to 1 circle. This circle is your conductance equal to 1 circle, right? So the procedure, what you're attempting to do, you're going to rotate this impedance. Okay, you're going to move this. This is going to be a circle around the origin. You're going to move this way with a section of transmission line, and then move it this way along a constant conductance line to the origin, right? By adding a parallel shorted stub, right? But the problem is on this Smith chart you only have one side. You don't have your conductance circles drawn out. So what you do, you use your resistance circles as a substitute for those by reflecting your impedance through a virtual quarter wavelength stub, like a quarter wavelength like length of transmission line. So what you do, I'll just quickly remove all of those. And what you do, you move this across to the opposite side. Where was this? This point was 0.7.
I think it's your ruler tool at the top.
Huh? Sorry?
There's a ruler tool.
Oh, okay. I'm not very familiar with this kind of thing. I just I draw the point from my. I have a Smith chart over here, so I'm just going to find the point manually. 0.7. This one is 0.5. So this point will be 0.5 intersection with 0.7. So. God. 0.5, 0.7. The point is going to be roughly here. So you move this point across here to use the to use the conductance circles effectively. So now like this diagram is in conductance. I'll probably just use different colors. This is in conductance mode. This is in impedance mode, right? And so what you do, you try to move around the origin until you touch like the conductance, like the conductance equals one circle, and then you add conductance in parallel to bring this to the origin, to conductance equal to 1, 0, right? You can find what this section is equal to. This is going to be, to make sure I draw it properly, is going to be intersection with 1.2 line. This point is going to be actually here. It's very hard to draw on a Smith chart without a ruler. This point is going to be like this. Ideally, we draw this with a ruler and compass in the exam. So I would highly recommend you to bring a compass in the exam. It makes a lot of difference. So this, I'll make an attempt to use, how do I? No, I will not use this. I don't know how to use this. I'll just eyeball this from like. This is supposed to be 0.11. It's supposed to be here. This is supposed to be here, and this point is supposed to be. This point is supposed to be 0.06. So it's 0.0. It's supposed to be here. Yeah, and then you add a step which adds 1.2 conductance in parallel. So I'll just draw this again. You have your load ZL. You add a section of line of some length. How is it called? Of some length Z. Then you add a shorted stub in parallel, which has an impedance, which has Y equal to minus 1.2 J. And then here you look and you see Z naught. Right? This length of cable D, it can be found just as a difference. Just like how much you need to rotate by. You can see that here is 0.11 and here is 0.17. This is supposed to be exactly through this 0.17. So the difference is this equal 0.06 lambda. And then how do you find L? L is this like is length of the stub. You need to find the stub which has a parallel conductance of 1.2 J. The minus sign comes from the fact that you flip the chart. It would normally be there. It wouldn't normally be there. Because adding inductive stub on this flipped chart means moving downwards, not upwards. So Z of the stub is equal to 1 over minus 1.2 J, which is equal to how much? Which is equal to 0. How much is it equal to? 0. Take the calculation. 8 something, 0.8 something. It's 0.83 roughly. J ohms from the stub charge that I have. And now the way you find length, you move from short end. So you have a shorter stub. You move from short. You move from short circuit end. You move around the chart until you hit that value of. Where was it?
Another question.
Yeah.
Isn't short circuit on right hand side?
short circuit is in this chart. It's on right because I should probably draw different colors. The blue graph. It is for conductance mode. So for blue blue lines, left hand side would be open and right hand side would be shorted because you are using a single sided Smith chart and you have to work in both conductances and impedances because you could add both shorted stubs like in series or in parallel. So you have to be able to work with both. So you have to keep track: are you in conductance mode or in impedance mode? By default, this is in impedance mode. So left hand side is shorted, right hand side is open, and which you can see by the numbers. So here numbers are high, here numbers are low. So left hand side is small resistance, so shorted, right? And so you move upward until you hit this inductance, 0.83 J ohms. Is it? Yes, 0.3 J ohms. Which actually here happens to be also 0.11. Similar to your assignment, which is not guaranteed with always the case, but here it just happens to be like the same length as your initial rotation. Like the initial rotation that you need to apply to your point. So L is equal to 0.11 lambda. And now you can convert those to actual centimeters by using the values that you found before. So this will because your lambda is equal to 8.63 centimeters. This will go to 0.518 centimeters, and this will be 0.949 centimeters. All good? Any questions? All good. I think for this question, this is it. I'll double check. Yes. Find small values of DNL in meters. You just convert to meters, and find the value. So this is it for the question. In the exam, you would. In the exam, you should label all the points in the Smith chart and write, this point corresponds to this, this point corresponds to that. Here, for sake of shortness, I'm not doing that. I probably should. So this is P1. I'll just label it in the corresponding colors. Hey, why is this? Okay, fine. P1, P2, P4. So P1 is initial load impedance. P2 it's flipped to conductance, to admittance, sorry. P3 is rotated to reach the unity conductance circle after length D of transmission line, and P4 is matched. All good? Any questions? Fine. P3 is here. It's after you rotated by length D of the transmission line. So it's where is it's at this point. As this impedance is corresponding to point P3. It's after the D, but before L. Any questions? All good? Then I'll move on to last question that I was planning to show, which is a question on waveguides. which was question 5 of last year's paper. Last question.
Oh, they're the same.
So here we have a rectangular waveguide with given dimensions. We have a waveguide. Its A is equal to 7.112 millimeters and B is equal to 3.556 millimeters. By convention, A is always horizontal dimension, so A is biggest dimension. It's convention. It can be like as a waveguide can be this way, but this is still A because it's convention. Why can I not use this? Fine. You can notice immediately that A is equal to twice B, which is actually very convenient because this is going to mean that if you can fit 1 lambda across B, you can fit 2 lambda across A, which means that, for example, your TE01 mode is going to have the same cutoff as TE20. And same for every multiple of those, which is fairly convenient for calculations in this case. The question asks to calculate the cutoff frequency of the lowest 5 modes of propagation, both T and TM modes. So the lowest mode we can propagate at any waveguide is TE01. And then in some order we're going to have TE10, TM11, TE11, then TE20, which is the same as, this is going to be the same as this, because of this fact. I will actually stack them together. This is going to be TE20, and this is going to be the frequency here. And those are the lowest 5 modes. The higher modes, like 02, 21, are obviously going to be higher frequencies. And the question only asks for 5 lowest, so I don't need to consider them. Formula for cutoff frequency, which we are given, I think, in the formula sheet. Is there a formula sheet? Oh, in the past paper there wasn't a formula sheet. But it's fairly easy to remember. It is written like this: 1/2 C, or VP C on ER, mu R. But here they are 1, so I am just going to ignore them. Times square root of M over A squared plus N over B squared. If you just have a single dimension, for example TE10 or TE20, right? Then you can just remove this part and it will reduce to FC is equal to 1/2 C index M on A, which corresponds to being able to fit M lambda on 2 transversely into the waveguide, which is basically like the cutoff condition for for the waveguide. If the waveguide is smaller than half a wavelength in all dimensions, it cannot propagate any modes as the frequency. And to propagate nth mode, you need to fit n half wavelengths. And this is how you would remember this formula. And this 1/2 comes from lambda on 2, essentially. The frequency is half as much. So let's move to the question. I will probably move all of this to the side. Hey. Oops. So for TE10, you just have in the formula m is equal to 1 and n is equal to 0. and this will just end up being 1/2 C 1 over A, which is, so if you plug in the calculator, you'll get 21.1 gigahertz. For those two modes, which are going to be equal frequency, you are going to have 42.2 gigahertz, which is exactly twice that because of the same like relationship in width and the height. And those modes are going to have 47.2 gigahertz. You get this number just you're plugging into the formula here. Like there are different indices of M and N. Then for the mode with lowest cutoff frequency, calculate the phase velocity and group velocity with F centered at 25 gigahertz. So first, phase velocity. Actually, I will also explain this briefly. So phase velocity, V phase is always greater than speed of light for TM or TE modes. And the group velocity is always smaller than speed of light. The reason for it is because if you imagine a waveguide as a metal tube of a sort, as a metal box, and say you have an antenna which excites some mode in the waveguide, and it propagates the modes outward. And then the modes are going to reflect over the sides. And then continue like this. So the wave travels, it reflects back and forth. And for example, if this wave encodes some kind of signal, the mean speed of travel along the waveguide is going to be smaller than speed of light because the wave doesn't travel in a straight line, it travels like this. So the mean speed of the signal will travel will be smaller. But phase velocity will counterintuitively be larger. The reason for this is because the peaks of the wave is like because those all because all those forward and backward waves are going to interfere with each other and produce peaks and troughs of the wave at at sizes smaller than the wavelengths. So like say this like this, a peak of the wave here, a peak of the wave here. The distance is going to be smaller than lambda because of how the waves interfere with each other, which will lead to apparent speed greater than the speed of light. But it actually doesn't respond to any propagation of the wave at all. It's just a standing wave pattern, interference pattern formed inside the waveguide by the incident reflected waves. This corresponds to phase velocity. The way you find phase velocity is a simple way to do it. Is through something called beta. Beta is wave number. It's basically frequency in space. How the same way t is period and frequency is 1 over period. Like this, lambda and the space frequency, which is called beta wave number, it's 1 over lambda. Actually, it's 2 pi over lambda. It's the same as omega is 2 pi over period. It's angular space frequency. So beta, let's define beta naught. It is the wave number of the wave in free space with no waveguide. So it's just 2 pi on lambda as a frequency. So this lambda is at 25 gigahertz. Actually, just a quick sanity check, 25 gigahertz is greater than 21 gigahertz. So this wave can actually travel at the lowest mode, which is just equal to 2 pi f on c. Because this is c on f, and 2 pi over this is 2 pi f on c, which is equal to 523 inverse meters. Beta is units is 1 over meter, the same as frequency is 1 over second. Then we find beta critical. It's the critical beta as a critical frequency, which is going to be, you use the same formula, but instead of f you use fc. You get 441.7 inverse meters. The wave is going to reflect over the waveguide like this. So if this is beta naught, and the critical wave you can sustain if the reflections are all going back and forth and not traveling forward. If the waveguide only fits half a wavelength, the wave is not going to propagate forward. It's going to travel up, down, and not going to go forward. So this corresponds to beta critical. So beta naught squared is just beta critical squared plus beta in the waveguide, beta propagation squared. So you can find the propagation beta here. It's just square root of beta naught squared minus a beta c squared, which is equal to 281.2 inverse meters. And this is going to be always smaller than beta in free space, because the phase velocity is always going to be bigger than the free space. And our critical our phase velocity, our speed of light, speed of the propagation of this wave, like judging by the peaks and troughs of the wave, is going to be equal to just 2 pi f over beta propagation by the same formula. And we will find that it's actually equal to 1.86 c, because beta prop is smaller than our beta naught. So we get a larger speed of light. Which actually this phase velocity will actually be equal to just c times beta naught over beta prop by the same which is equal to just c divided by cosine theta, which where theta is this propagation angle, right? Yeah. So this answers the question about phase velocity. Oops. We need to find group velocity, which is always smaller than speed of light. If you how do I explain this? Actually, that's fine. I don't even need to explain this. Group velocity is the velocity that a signal would travel. Imagine rather than just like a steady state, like flat wave, like you send some kind of modulated signal. For example, like you do air modulation and send a pulse, like some pulse down the waveguide, and this pulse, instead of going straight, it's going to here is your pulse. It's going to travel here, and then going to reflect backward. And the average speed, the average speed of of this pulse in the waveguide is going to be smaller than speed of light. Actually, it's going to be V group is just going to be c times cosine theta. It's going to be smaller by the same factor. You can normally the way it is defined, you send some narrow band signal down the waveguide, some modulated narrow band signal, and you find how quickly each mode travels, and then you find that group velocity is equal to just d beta prop over d omega inverse of that at omega equal to your 25 gigahertz at your 2 pi times 25 gigahertz. But then this will actually just boil down to this. So if you draw like this, this is your frequency, and this is your FC. You draw both Vg and V phase as function of frequency. At frequency equal to Fc, group velocity is just going to be 0. And then it's going to slowly increase up to c. This asymptote here is going to be the speed of light in vacuum. This is c. While the phase velocity is going to start out infinite and then go down to c as well. Understand? Any questions? And this will actually be equal to 0.537 C. As a quick life hack of sorts, because beta is proportional to frequency and C is constant and 2 pi is also constant, beta not the beta prop is the same as F over FC. So you can just use the frequency division to get this. Yeah?
What's the point of the phase velocity?
The point of phase velocity? It does really have a point. Actually, I'll just quickly give you an example. An example I think I gave in the crash course, which illustrates this very well. Like this, like a phenomenon in the atmosphere called ELF pulse. It's like when you have a lightning, it sends a relativistic pulse into the air, and then so here you have a lightning to ground, and here's your cloud. It sends a pulse, and then the pulse goes to ionosphere. This is ionosphere, and then this pulse is going to ionize, the atoms of air in the ionosphere and produce this very faint glow. As the wave travels, it's going to ionize the air here, and you will see a glowing ring around this. You will see like a ring of glowing air above the lightning, right? Very, very high above lightning. This is very dim glow, so it's very not noticeable, like usually. And usually the cloud is above you. If you stand here, you can't really see this. But like this, the satellites can see this kind of glow, and this, the instruments you can record this. The thing is that the wave travels outward at speed of light, but this ring travels outward at speed higher than speed of light, at apparent speed higher than speed of light. So this ring will expand at speed higher than c, much higher than c, because it's actually the tangent of this circular wavefront. This is the phase velocity. This is what phase velocity means. It's the speed at which peaks of the wave travel in some medium, right? This does not correspond to actual movement of any material or any energy. It is just a fictional speed at which some peak of something travels. It does need to represent any information or any signal, right?
So, could you get infinite speed of outwards propagation of that light circles of the light?
Yes.
If the frequency was just really, really high. If the frequency of the pulse emitted from the lightning above the cloud was
it's not about frequency. It's about the shape of the wavefront. Because here it's just a single pulse. That's frequency. It's just a single pulse. It's like this. It doesn't have it has a little bit of oscillation, but it's just a single pulse normally. So this is just a single wavefront. So you actually get infinite speed of this light source right at the point where the wavefront hits the ionosphere, because here the tangent is flat, right?
Yeah.
So this thing is going to expand infinitely fast at this single point, but then it's going to slow down.
Yeah.
And as the wavefront becomes like this, it's going to propagate at the same speed as speed of light, right? So this is what phase velocity means. It's just a speed of propagation of some fictional peak of the wave, of some interference pattern that we see in some medium, right? Understand? Any questions? All good? I think I can just end then, because this is all the questions I've prepared, and we're a bit over time. So
Thank you very much.
Let's end the stream. As always, everyone online, best of luck with your studies. Good luck with the exams. And yeah, should be a good one. Goodbye.